Determine all intervals of concave up or concave down and determine the coordinates of all inflection points, including cliffs, for the function f of x equals x squared plus 2 sine x. The first thing to do is find the domain. F of x equals x squared, a polynomial term, the domain will be all real numbers, plus 2 times sine x, a trig function with no denominator, the domain will also be all real numbers, so collectively the domain is all real numbers, or negative infinity to positive infinity. A trig function has a tendency to have an infinite number of inflection points if it has any at all, as well as an infinite number of concave up or concave down intervals. But nicely, sine x is 2 pi periodic, which means that it repeats itself every 2 pi radians. This can also be written as f of x plus 2 pi equals f of x. So instead of working on the entire domain of negative infinity to positive infinity, which can be a little overwhelming, we can instead work on the unit circle interval, which begins at 0. It includes its square bracket up to 2 pi. It does not include its round bracket because 2 pi is the same point as 0 on the unit circle. Find all results on the unit circle interval, and then extend the results to the entire domain using the 2 pi periodic nature of sine x. The next thing to do is find all candidate numbers. We will need the second derivative for this. We will start with the first derivative. F prime x equals, the derivative of x squared is 2x, plus 2 times the derivative of sine x is cosine x. We can now find the second derivative. The derivative of 2x will be 2, plus 2 times the derivative of cosine x, which is negative sine x. In the second term, positive times negative is negative. There's a 2, and there's also a sine x. We can now set the numerator equal to 0, and the denominator, if there is one, also equal to 0, and solve for all x's that make it true. Let's start by subtracting 2 from both sides, so negative 2 sine x equals 2, negative 2. We can now divide both sides by negative 2, so sine x equals 2, positive 1. This happens only one time on the unit circle interval. Sine x equals to positive 1 at pi over 2. We can now draw a unit circle interval line, a line representing the unit circle interval. It begins at 0 and goes all the way to 2 pi. It includes the 0, so square bracket on the 0. It does not include the 2 pi, round bracket on the 2 pi. We can put any candidate numbers on here. We have pi over 2 is the only candidate number, which splits the unit circle interval into 2 separate intervals. We can pick a test value in each of the intervals. The first interval is 0 to pi over 2, which is the first quadrant. We can pick pi over 4 in the first quadrant of the unit circle. The next interval is pi over 2 all the way to 2 pi, which encompasses the second, third, and fourth quadrants. We can pick pi within there. We can now test the concavity in each of these intervals by plugging the test value into the second derivative. We don't care about the value of the second derivative, just whether it is positive or negative. So plugging in the test value into the second derivative, pi over 4. The sine of pi over 4 is square root of 2 over 2. Times the 2 is square root of 2. So we have 2 minus the square root of 2. 2 is bigger than the square root of 2, so that will be a positive number. We have a positive second derivative. This corresponds to concave up. Plugging pi in to the second derivative, the sine of pi is a 0. 2 times 0 is 0, so we have 2 minus 0, which is a positive number. We have a positive second derivative, which corresponds to concave up. The left endpoint here is included, this 0. And that's because 2 pi, the right endpoint, which is not included, is equivalent due to the 2 pi periodic nature of sine x. And that means that these two intervals connect onto each other because this repeats itself every 2 pi radians. And that means this concave up interval will also exist over here to the left of the 0. This interval has a width of pi over 2 to 2 pi. 2 pi is 4 pi over 2. Pi over 2 to 4 pi over 2 has a width of 3 pi over 2. So there's an interval to the left of 0 of width 3 pi over 2 that is also concave up that connects onto it. And that means that it will be concave up starting from 3 pi over 2 to the left of 0, which is negative 3 pi over 2, all the way up to positive pi over 2. That will be this entire interval over here to the left of it plus this entire interval connected together. And that will account for the entire interval of concave up. Right at the candidate number of x equals pi over 2, the concavity is concave up on the left and concave up on the right. It's not changing. And so pi over 2 will not be an inflection point, and pi over 2 is the only candidate number here. And therefore, there are no other candidates to be inflection points, and since pi over 2 is not an inflection point, there are no inflection points. In general, trig functions either have an infinite number of inflection points or they have no inflection points. This is the results over that interval. We can now expand these results to the entire domain of negative infinity to positive infinity using the 2 pi periodic nature of sine x by adding to each of the x values the period 2 pi times an integer n. This concave up interval is an interval of x values, so we will add 2 pi, the period, times n, an integer, to each of them. There are no inflection points, so there will be no inflection points over the entire domain. So we have concave up starting at negative 3 pi over 2 plus the period 2 pi times an integer n up to pi over 2 plus 2 pi times an integer n. And we have no inflection points. Where n here is any integer. It can be a positive integer. It can be a negative integer. It can even be 0. If n equals 0, it'll give the results over the interval we just worked with, allowing n to be any integer. We'll extend those results to the entire domain of negative infinity to positive infinity.